Mm. Mm. Oh. Mm. Okay, as I told you before, due to my business trip to Kyoto, Japan, I have to record my lecture 25th and 26th, and this is the first one, lecture 25th for quantum effect. So let's go. Okay, in the previous lecture, we have thought about the general consideration about quantum effect. So I introduced the concept of subbands, and in the case of a silicon conduction band, we can uh, find six valleys, and inside these six valleys, even uh, due to geometric confinement or electrical confinement, we can find some quantized states, and they are called as sub bands. So you can find this sub bands concept in our previous lecture, and now we wanted to do some approximations for this electrons, these electrons inside MOS channel. So as I told you before, in order to be more precise, we have to consider the Schrödinger-Poisson equation. However, this is far beyond in the far beyond the scope of this lecture. Instead, we wanted to just to do some approximations. So maybe you remember that in the previous lecture, the last part was devoted to the shape of this potential well. In this triangular potential well, we assume linear variation of our potential inside this silicon part. Of course, this is corresponding to silicon dioxide. And as I told you before, if we wanted to be more exact, then we have to consider this parabolic behavior. However, uh, anyhow, there is no electron in this area, so errors in the potential in this extremely high potential value doesn't make any sense, any change in the calculated subband energy. So that's the reason why we just take these linear approximations. Okay, so this one approximated as a linear potential, so now we have really a triangular potential well, and of course we expect that we can find the electrons mainly in this well, the deep side of this well, and maybe there will be almost no chance for us to find electrons in this part. Then just to write down Schrödinger equation, and now we can see this one. No, this one is corresponding to the kinetic energy of our electron, and this part is corresponding to the potential energy of our electron. So you can see that the potential energy is assumed to be q times surface electric field, and this is a position. So simply speaking, at interface we have zero potential, and if we go to further and further or deeper and deeper into the substrate, then we believe that potential energy felt by our electrons increase. So this part becomes less probable, favorable for electrons. So now we wanted to have a certain electron density only nearby this interface part, and sum of kinetic energy and potential energy should be the total energy E. So that is simply the Schrödinger equation. So the goal is to find out a certain eigenvector psi. This is the eigenvector or eigenfunction, and here we have eigenvalue, eigenenergy. So we wanted to find a pair of eigenvector and eigenvalue. So this is the Schrödinger equation. So if we consider a certain electron, then maybe this kinetic energy is more or less given, means that not exactly its value, but its operator form is given as this form. So however, depending on the problem, so we can have very different potential energy. For example, if we have this potential and if we have this potential, then of course, although we inserted the same electron into those wells, but the expected behavior of these two electrons will be completely different. So that's the reason why this V plays a critical role in this case. Well, now think about this one. In the case of our double gate MOSFET, how does it look like? So in this case, now our double gate MOSFET, so the size, or more exactly the nanosheet MOSFET, the thickness of this silicon layer is about 5 nanometer. And how does it look like in this case? Now we may have this flat potential or some other potential like this, but that doesn't much matter, because nowadays this 5 nanometer itself is already quite short. So in this case, geometric scattering, geometric confinement plays a major role to determine the behavior of our electrons. But please, let's come back to our planar MOSFET case. Then actually the size of this physical size of this silicon substrate is orders of micrometer. So this is much wider. So only confinement, this confinement is coming from this potential energy. So in this case, electrical field plays quite a significant role in determination of those levels. So by the way, here you can see the mass, and this mass is mxx, and this is corresponding to the x directional mass. And what is the x directional? So in our convention, we take this x as a vertical direction, where we can see the vertical MOS structure, MON silicon. This is taken as the x coordinate. So now the confinement is related with this vertical direction, so we have to take the mass, directional mass, along the x direction. Of course, for example, if we consider the confinement along y direction, then of course in that case we have to use y directional mass. But in this case we have to use x directional mass. Okay, then how can you solve this one? actually whether we can solve the Schrödinger equation or not analytically, that is determined by the potential. There are only a small number of problems we have the analytic solution. In many cases, the calculation of or solution of the Schrödinger equation is not available in analytic way, so we must solve it by numerical way. But fortunately, this triangular potential well gives us the really available analytically available solution. So that's the reason why we wanted to approximate the complicated potential well as just a simple triangular well. So in this slide, I just summarize how can we understand its solution. So let me just quickly go to this slide. So its solution is given as L function. This is the name of its so this is a name of one person's name, and now you can have this function L function. This is a function of x, and it is given as this seemingly quite complicated integral. Where can you find the x? So here we have x, and it is integrated over t, please, not over x but over t. So eventually t goes away and we have only x dependence. Then if we draw this L function, so this is x-axis and this is it's a L function, and you can see that it is oscillating in its seemingly negative value, and if we goes to the positive one, then that is decreasing to 0. So this is the area function. So of course, area function, there is another area function, usually write down not in this AI, but this is a second type, so this is called as a BI function. But we do not consider this BI function because this BI function is diverging when we go to x equal to positive infinity. So from the physical consideration, we expect that if we go to the deep into the substrate, the wave function should vanish. However, if we take this BI function, then we cannot satisfy that boundary condition. That's the reason why we just take this first one, AI function, and its shape is, as I told you before, shown here. So if this AI is really the function of our Schrödinger equation, if that is the solution of the Schrödinger equation, then what we have to do is like this. So if psi wave function follows this L function, then we have to show second derivative of AI function times xai equal to some coefficient n AI or something like that. So we have to have this kind of consideration. So that's the reason why I just take the second order derivative of AI function, and we'll see what happens to this guy. So here I just calculated its second derivative. Okay, this function itself is given as a form of integration, so we must keep this form. And when we take the derivative with respect to the x, then actually we can take just second derivative of this cosine function. After that, we can just take integration. So when we take this cosine function, and here we have a minus sign due to second derivative, also due to this xt term, we have t squared term, and the same cosine function. You know, when we take derivative twice for sinusoidal functions like sine or cosine, it generates itself and negative sign. Okay, so that's the reason why we have this form. Then how can we calculate this integral? It will be a little difficult. However, now we can understand this identity. So what is it? Here we have t squared and cosine function. This is a t squared cosine function, and if we multiply x to our original cosine function and sum them all, then that is generating the overall derivative of our sinusoidal function with respect to the t, the parameter. So simply speaking, if we multiply x and x in this case and sum these two equations, then we will have this integration over certain d over dt of a sine function, and that gives you just number 0. So please check this equation, and the reason why I introduced here certain note is here we have the upper limit of a positive infinity, and if we just follow this form, then of course this one will give us this one sine function evaluated at x equal positive and minus a sine evaluated at not x equal positive, t equal to positive and t equal to 0. When t equal to 0, sine function vanishes, so it's okay, it's gone. And you know, in the case of t equal to infinity or t approach to infinity, then now this t and t, cube over t and linear over t, so increase quite rapidly. So if we go to the extreme of a very high t value, actually this sine function or the upper limit value will fluctuating quite rapidly. So in this case, this value is regarded as 0, and here you have just number 0. So that is not that conventional, at least from my own experience. So anyway, that's the reason why we have number 0. Simply speaking, this AI function, so L function, satisfy just homogeneity when evaluate this operation. So takes the second derivative and multiply x and sum these two terms, then we will have just number 0. Wow, then is it really corresponding to this wave function? So unfortunately, in this case we have some numbers Hava square over 2 directional mass, and here also we have q times surface electric field, so that makes a certain complication. So we have to introduce a little bit more variable transformations, scaling. So now let's come back. Schrödinger equation in its original form is shown here. What is the difference? Because we have just a vanishing term in the right hand side, so intentionally we introduce the vanishing right hand side term. So the E times psi is just moved into the left hand side, so now we have this form, you can easily check that this is corresponding to the original, just scaled version or manipulated version of Schrödinger equation. I didn't make any trick. So after that, still we have if yes. Oh, so I made a mistake. So here I must introduce a minus sign. Sorry about that. And also here we have a minus sign. Yes, so sorry about that. I made mistakes in minus sign. So here we have a minus sign. Anyway, take the second derivative and multiply minus x. That is corresponding to the area function, but here you can see that the factor is not exactly corresponding to the x. It has a certain coefficient and also offset, so it's not that very comfortable. So we introduce a little variable transformation. So first of all, this factor is denoted as a cube over alpha, and also we have a certain offset value. And now when we introduce a psi value, so from position value to this psi value, then now we can see that this Schrödinger equation can be written as this reformulated form. So now the solution of this this psi is simply follows area function in terms of this psi variable. Of course, this is defined as this form, so eventually it can be written as a function of our usual coefficient or coordinate x. Okay, so that is shown here. Now psi follows this form. Well, you can find that here proportionality, or actually this is a similarity, but that is regarded as a proportionality. Since this is a eigenvalue problem, actually this normalization coefficient is not that important in this context, so we will just leave it here. But anyway, we can normalize it later if we want. So now that's it. We have solved for this triangular potential well, this Schrödinger equation. Simply speaking, psi, which is a function of position, can be written as area function, and it is alpha x minus certain offset values. So if you have, for example, I have 1 nanometer, then just put 1 nanometer here and calculate your alpha and energy value. Oh, I don't have any energy value, so this is an unknown value. Yes, so I will discuss it later. So right now we have no idea about what is the actual energy value. Yes, we don't have. And this is a surface electric field. In this case, we assume a certain given value of a surface electric field, because by determining this one, we just define or determine the slope of our potential well, so that should be given. So this is the solution, but as I discussed in the previous discussion, the energy is right now unknown. So which value of E should be used for this this wave function? So it is given as satisfying the boundary condition. At the interface, the wave function must vanish. So, for example, let's say that this one. So this is, although this is x, then now we can convert it to certain psi value. So let's say that although this is corresponding to x equal to 0, if we consider this psi value, then this is simply given as minus alpha q electric field and E. So there is no guarantee that x equal to 0 is corresponding to psi equal to 0. Actually, the value is determined by this energy level. So let's say that let's say that by selecting certain value of energy value, for example, let's assume that our x equal to 0 is corresponding to this way, then we means that our electron wave function just oscillating in that way, and at x equal to 0 we have a non-vanishing wave function that is clearly disobeying the boundary condition. So simply speaking, where can you find the values, wave functions? So this one can be an allowed wave function, or this one can be another allowed wave function, or this one, or that one. You can find so many available solutions, but all of them share one point. At x equal to 0, we must have the vanishing wave function. So by applying this boundary condition, we can quickly find that this form. So this is corresponding to x equal to 0, and in that case our overall input argument for every function should be a 0 of every function. It means that here, when a 1 value is inserted, then we have a 0, a2, a3, so we have a 0, 0, 0. So a sub j is regarded as zeros of the every function, and it's in its how can say, it's an absolute value. The lowest one is denoted as a naught, and its value is minus 2 point something, and it is increasing. So simply speaking, I'm saying that this point is corresponding to a0, a1, a2, a3, something like that. So so in order to satisfy the boundary condition at x equals 0, the result is E should be quantized. We cannot expect a continuous spectrum of E values. Instead, E value is just discretely distributed. So there is a first E value, second E value, another energy level, which can be allowed from this system. So each eigen value is corresponding to the each subband. So simply speaking, you can find this one, and this is not my invention. So people already did some works, and zeros of the L functions are well approximated this simple form. So how did you find it? So I don't have any idea about it. it is a known form to describe the zeros of eigen zeros of airy functions. And when we estimate the errors introduced by this approximation and the real value, actually it's not that high. Its error is maximum when we have a equal to 0, and when we go to even higher value, so it becomes even smaller. So simply speaking, you can just rely on this approximate. Please, this is an approximate expression, good enough approximate expression, and then now we can understand eigenenergy is given as this form. Okay, please check this one. It means that when we have lowest energy J equal to 0, then we will have a certain energy. And if we go to the second one, then we will have a little increased energy level. So if we go to higher and higher index for J quantum number, then we will have higher and higher energy. This is quite expected behavior. And let's think about another dependency. So these are just the universal constant and mass. Here we have mass and electric field, surface electric field. Of course, if we have steep potential well and very wide potential well, what will happen? This is corresponding to surface electric field much higher than surface electric field much lower. In this case, if this is a large number, then we will have quite a high E0 value. So we will have, for example, starting in this way. However, in this case, we will have the energy start, the ground energy start at very low case. So simply speaking, if we introduce by very tight confinement or narrow, confined in a very narrow region, then our energy space, ground energy value can be higher. And also, since this is affecting to all of our values, so the energy spacing between neighboring or nearest energy values will be increased. So it means that now we have quite high difference or large difference. So compared with this relatively small difference in its energy level. So do not consider this one is the exact value, but just illustration. Another one is here, these are all numbers. However, another important quantity is x directional mesh. And as I told you before in our previous lecture 24, so we have 6 copies of silicon conduction band bellies. So although they are all identical, but they are lying at different axes. So here we have 3 different principal axes, and we have different directional mesh. For example, let's say that this is happen to be the direction of confinement, the x direction. Then what will happen? For these 2 bellies shown here and there, they exhibit so the value of a directional mesh, so confinement direction, which is corresponding to very high number, so longitudinal mass, so called. However, if we consider other 4 bellies, like this guy and that guy and another one and another one, of course you can say that these two makes a pair, and these two makes another pair, and they are not identical. Yes, in terms of the entire masses, they are not identical. However, if we just consider the confinement mass along that direction, that direction, and that direction, and that direction, although, so you know where the longitudinal mass, this long axis is aligned, that is different. However, from the vertical point of view, all of them shows a short distance corresponding to relatively small mass mxx equal to 0.19 electron less mass. So that's the reason why in the last statement in this slide there are two different confinement mass values. This one, which is high, that is corresponding to these two values, and there are two copies, so that's the reason why we call the degeneracy factor of 2. And there are another 4 values, 1, 2, 3, 4, and they have a relatively low mass. Okay, so now we have two different categories. And now what we can expect is, since this is high mass, so now E naught prime originated from mxx equal to 0.91 m naught, and mxx corresponding to 0.19 m0. Which one is higher and which one is lower? Since this mass is found in the lower part of this expression, you can see that now this is the expected behavior of two ground states. So simply speaking, in this consideration, the most important one is the lowest energy level and who takes the lowest energy level. So simply speaking, we can find that this one takes the lowest energy level. So heavy mass, just heavy confinement mass takes the lowest energy level. So simply speaking here, although we have 6 different values here, but in terms of energetic occupancy, so which one is most dominant in taking electrons, these two are most relevant, and other 4 will contribute less importantly when we have a severe confinement effect. Okay. So now from this understanding, now we can try to calculate total inversion charge per unit area. So here total means that inversion charge can be contributed two different Belli types. Belli type 1 and Belli type 2 equal to G equal to 2 and G prime equal to 4. So this is prime one and unprimed one, and of course it can have many different subbands. So contribution from these subbands and contribution from also these subbands, both of them contribute to the total inversion charge, so we have to calculate it. But before talking about this calculation procedure, please think about what the motivation of this discussion. Why we are trying to calculate this total inversion charge? We already know that there is a certain electron density, and it is given as the surface electric field. So if we have a surface electric field and surface potential, now we can have a full understanding on the behavior of our MOS capacitor. But why we do introduce once again this expression is because our previous discussion omitted or neglected the quantum effect. So now we wanted to introduce a new expression which is consistent with the quantum confinement effect. So for a solvent, so when we have a given value and given quantum number J, we can calculate the number of electrons coming from this solvent in this way. This is corresponding to, here we have a Z value, this is just degeneracy. So for example, it can be either 2 or 4. So now we understand, and all of them are just given numbers. And you know, here we have M, Y, M, Z. What is this? These are corresponding to Y directional, Z directional mass. Oh, up to now we just consider X directional mass. Yes, you are right. So in the solution of a Schrödinger equation, we only consider X directional mass. So then why we need My and Mz, which are perpendicular to this confinement direction? So these two numbers are required to calculate density of states. So this is corresponding to the density of state of this 2D material, 2D electron gas. For more completed discussion, so please see this textbook or other kinds of references. After that, now we have this expression. This expression is obtained from integrating our Fermi-Dirac distribution, whose Fermi level is given as EF, and this E mean is the subband minimum energy. Subband minimum energy. So yes, that's it. However, please note that this is the contribution from a single subband. We have to understand there are several subbands for a belly. So also we have two different types of bellies. So that's the reason why. So summation of subbands finally gives us this form. Here we have just the leading coefficient, and now you can see here, see, degeneracies. So this is corresponding to unprimed ladder, and this is primed ladder. So typically, so people use the term like the ladder to show the collection of energy levels for given belly. So here we have unprimed ladder, and this is a primed ladder, but it doesn't matter. Anyway, now here we have 2 and 4, and we have to calculate My and Mg product and take its square root. So if we go to this unprimed bellies, so although vertical one is heavy, but for in plane ones along that these two directions, we have short distance corresponding to just transversal mass or 0.19 m0. So since they are the same, so we can quickly say that this is corresponding to just mt. Here mt is nothing but just 0.19 m0. On the other hand, if we go to the primed ladder, in this case you can see that along one direction we have a longitudinal mass, and along the other direction we have a transversal mass. So we have to calculate ml multiplied by mt and its square root, even when it is rotated by 90 degrees. But in this case, now we have mt times ml, which are identical, so we can just use it in here. Yes. And also we have finally the summation of subbands. Here J is for the letters or subbands for unprimed ladder, and this J is for subband inside the primed ladder. And here we have EF. This is formulable. And what is this? Now here we have to give the subband minimum energy. And where can you find this subband minimum energy? So please, this is corresponding to subband minimum energy is given as EC prime plus EJ. You know that EJ, so with the quantum number of J, this is the energy measured from this point. So energy is just reference at this point, because when we insert x equal to 0, then v equal to 0. So this is regarded as the reference energy of our calculation. So now we understand this is EJ for all subband, but in the case of calculation of electron density, so now reference should be changed. And that's the reason why now we must consider what is this reference energy level. In that case, reference energy level is just denoted by Professor Tower EC prime. So that's the reason why here I just introduce EC prime. So this EC prime should be regarded as the conduction band energy at x equal to 0, and at the same time it is the minimum value of conduction band energy. So now we have this analytic expression for overall inversion layer charge. Okay, so then it is really good to have this expression, but from this expression what we can expect. So let's try to draw some meaningful information. When we have a sub-threshold region, then what we can do is here. So when we have a look at, for example, this first term, now in this calculation we have this quite a complicated term. First, evaluate the exponential and add 1. Once again, take the logarithm. So that is quite much complicated, but let's just say this way. log of 1 plus x. So this x is by definition exponential and kbt and ef minus e servant minimum energy. So in general we have to calculate this one. However, let's assume that we are currently considering sub-threshold region. This means that compared with our EF value, our sub-band minimum values are far beyond that. So this is the typical case in sub-threshold region. Why? If this is not the case, let's say that E mean is comparable to EF, then what will happen? Actually, this subband will be almost fully occupied, so it can contribute to quite high electron density to our inversion channel. Then our assumption of a sub-threshold region is disobeyed. So that's the reason why we can assume that E mean is much higher than EF value. Simply speaking, this value, this input argument of exponential function is much lower than number 0. This is a negative value, so this value would be very close to number 0. In this case, actually we can approximate this log of 1 plus x as just x. So in that case, now complicated logarithmic function goes away, and now we have just exponential dependence. Good. So in this case, now after some manipulation, now you can see that here we have exponential dependence over our electron density, or the charge due to the electron density, which is exponentially dependent on surface potential. Yes, so it is quite much expected, but point is now the leading coefficient is not that easy, so it is more complicated and different from the semi-classical one. So what does it mean? So compared with the semi-classical one, we have different expressions. So even when the potential is the same on the fixed potential profile, our electron charge calculated with quantum mechanical consideration will be smaller than its classical counterpart. So that is shown here. Example taken from our textbook. So for example, when doping, substrate doping is 3 times 10 to the 18 per cubic centimeter, so then additional surface potential to match the classical density is about 0.13 volt. So it means that when we consider quantum mechanical effect, actually the effective capacity of our inversion layer is reduced. So we, in order to get the same amount of electrons, we have to introduce additional banding. So so let me just give you just a visual expression. This is sorry about that, this is not for planar MOSFET. So this is obtained from double gate MOS structure, so sorry about that, but anyway you can see the difference. So here we have empty symbols and empty symbols and field symbols. So here this is empty, and of course this is also empty, and this is a field, and this is a field. So here we have a red and blue, but just to consider one single color. For example, let's consider red one. So this is corresponding to classical. So without quantum effect, the result for integrated electron density as a function of a certain gate voltage. This is the one we have studied up to now. And compared with this classical one, the one with quantum effect, then now you can see that the shape is somewhat different. So what is the difference? So when we apply a given gate voltage, now we can see that we have less electron density collected in our MOS structure. So we need, in order to get the same amount of electron density, we need additional gate voltage. So by applying additional voltage, so we introduce even higher surface potential, and that compensated the reduced capacity of our inversion layer. So that is one thing. And I think that the second part is already discussed in our previous lecture, but let me just repeat once again. This figure is taken from Professor Tower's textbook, but its original version is already shown in the original text, original paper. So here we have 6 different curves, but just to compare one pair, this is corresponding to a certain device, and this is corresponding to the same device. However, this calculation is done without quantum mechanical effect, and this upper curve is calculated from quantum mechanical consideration. What is this? The difference value is corresponding to average inversion layer depth. It means that now here we have silicon dioxide and silicon, and when we have a certain electron density shown here, and this distance is measured. So in the case of semi-classical expression, it is just almost exponentially decaying. So when we take just the average of the distance, it is not exactly 0, because here we have some portion. However, this is much shorter than quantum mechanical counterpart. So now you can see that this is corresponding to our previous lecture or previous contents calculated from classical calculation, and this additional distance is used as the increased effective thickness of oxide layer. So this is quite much important. So similar calculation has been done also in double gate MOS structure, and it really depends on the operational regime. So area electron density. Usually, think about this one. How can you increase the electron density? In order to increase electron density, so starting from this one, by applying even higher and higher gate bias, so now we can make our potential well narrower and narrower. In this case, since it becomes more narrower, so compared with this original one, which is widely distributed, now we must have more confined electron. So this peak point or average point is moving toward the interface. That's the reason why we have a reduction of a distance when we go to higher and higher effective field. So actually modeling this effect is quite important even for double gate MOSFET or other kinds of multi-gate structures. Okay. So anyway, let me just summarize. So in this lecture, in the previous lecture and today's lecture, lecture 25, we have studied about quantum mechanical effect. So simply speaking, due to the geometrical confinement and electrical confinement, of course, geometrical confinement is related to the double gate or nanosheet devices, not for planar MOSFETs. But anyway, when we have a certain confinement, then electron should show certain subband structure. So that really happens in our MOS inversion layer, and the confinement is occurs along vertical direction. So therefore, vertical directional mass, x directional mass is important, and we can categorize two different ladders. One is the one with heavier mass, so unprimed ladder whose mass is almost about 0.9 m naught, and another one is a primed ladder whose mass, confinement mass, is much smaller, like just 0.19 m0 in this case. So now we have two different contributions or two different ladders, and each of them contribute to electron density. And yes, so depending on the subband structure, they have different numbers. But point is, when we consider subthreshold region, then now we can understand the electron density obtained from this quantum mechanical constellation is smaller than its classical counterpart. So actually, compared with semi-classical theory, we must apply a little bit higher gate voltage to get the expected electron density. And since we have also distance, non-vanishing distance from the interface, so effective oxide thickness is getting larger when we consider quantum mechanical effect. So these two effects should be considered when we rigorously model this structure. Okay, so let me just summarize in this way. And now we have about about 10 minutes slightly. So the last lecture, lecture 26, will be devoted to the models for analytic models for double gate. But before talking about the double gate, so in this lecture, lecture 25, I just repeat my previous discussion about the technological relevance of a double gate approximation. So why we can treat the nanosheet as a double gate MOSFET, or not exactly, but we just wanted to justify our simplification. So please have a look at this one. These two graphs are taken from very famous paper by IBM, VLSI 2017. So it is already 8 years ago. And please note that at the time we were around 7 nanometer node and moved to 5 nanometer node, and this paper actually proposed the way to make make the technology suitable for sub 5 nanometer technology. So here you can see this is a typical FinFET case. In this case, within certain given length scale, 50 nanometer, we integrate 3 different fins. Of course, in this case, the effective area will be given as this perimeter. Okay, this is taken as a reference. But people think that now soon the end of FinFET technology will come, then we have to move to nano wire. Although there is nothing like nanowire in this caption, but this is corresponding to the nanowire, because everybody know that nanowire is much better than FinFET in terms of gate controllability. So now let's try. This is a nanowire, this is a nanowire, and yes, we have introduced nanowires within given area or given length scale, 50 nanometer. So this is a cross-sectional view, and where is a source and drain? Source and drain, that channel axis is laid in this vertical direction on your screen, so you are just looking at the cross section. And now you can see that in this case, actually, if we introduce it in that way, then increase of effective width, some of these perimeters are not that much high. However, let's go to the same length scale, but if we just introduce nano sheet instead of nano wire shown here, then of course we introduce additional silicon channel here and here and here. Yes, these are additional part, and of course we lost this part, but anyway we have additional silicon part, and increase is given as this length is increased and this length is lost. So when we measure just the effective width, and we can find that there exists 1.3 times higher. So please, when you consider nanowire, actually effective width does not grow rapidly, but by introducing this scheme, nanosheet, which has a high aspect ratio, then now we can effectively increase the width. Then of course the question is, this is quite obvious from just a geometric consideration, but obviously nanowire has better capability to get the short channel immunity, and this one will have lower capability. Yes, that's true, still that's true, but so in this paper they just evaluated the advantages of this nanowire and nanosheet, and they have found that actually gate controllability is already good for this nanosheet structure, and more important one is area efficiency. That was the conclusion of this paper. So this paper simply concludes that now we must use nanosheet transistor as a practical candidate technological option for next generation technology, and that was adopted. So nowadays we are working with a nanosheet instead of a nanowire. Okay, so this one shows the same one. So starting from FinFET, if we have the same width, then by adopting this C options, nanosheet options, we can increase this effective width quite a lot. However, the nanowire option, so this one is a nanowire option. When we have this nanowire option, actually it is not that much different from FinFET, and we have no additional advantages in terms of area efficiency. So now currently our devices always looks like this one, and now length scale is yes 50, and this is typically 5. So of course I'm not saying that always the drone width is 50 nanometer, so it's not. In reality we can change it, and the smallest one would be even orders of 10 something nanometer. And even for this case, so the ratio is 5 and 10 something, so at least 1 to 3, and in many cases is even higher values. So simply speaking, in a geometric constellation, so contribution from this length scale and contribution from this length scale, yes, this part is much more dominant, so it is good approximation to treat our nanosheet device as just a little bit modified double gate MOSFET. So simply a wide nanosheet can be considered as a double gate, and actually we have a wide nanosheet. So yes, so in this case, since we have extremely thin silicon channel, so silicon film is usually only lightly doped and fully depleted. Actually, whether you doped or not doesn't make a big difference in its electrical behavior, but usually we introduce a lightly doped and fully depleted. They are fully depleted means that we don't have to consider hole inside the system, so we can just consider electron and relatively low density of doping density. So in the last lecture 26, I will just introduce some analytical models proposed by Professor Tower, the author of our textbook, but please note that this one, performance advantages of a double gate MOSFET lies mainly in its short channel immunity compared with planar MOSFET. All of our journey is related with controlling the short channel effect, because that allows us integrate more chips into the system, of course, but ultimate goal is area efficiency. So whether we have to reduce actually the channel length or source drain length, whatever, actually from the viewpoint of a circuit designer, that doesn't matter. But from the device engineers, so there are not many technological options to scale down our devices. So scaling of channel length is the most powerful way to scale down our device, the most fundamental way to scale down our device. That's the reason why we always try to scale down the channel length. Okay, so now we have only one remaining lecture, and maybe I will record it in tomorrow morning, so and we'll release it in the next Wednesday. Thank you.